Welcome back. So last lecture video we studied the 4-noded 2D element, a 4-noded isoparametric 2D element. So that kind of element can be extended to higher order elements. So for example, what we studied last time was any irregular quadrilateral element, something like this one, can be transformed into a square element. So the original xy coordinate system is being converted into a xy eta system, and the original quadrilateral of irregular shape is being converted into a square, such that the size is 2 units in this xy direction and 2 units in eta direction. Let us say instead of this quadrilateral, if we had say 9-noded element, so this is higher order elements, the element could be something like this. So some element something like this one, which has this shape. The sides are not a straight line. So as you can see here, it can be a quadratic sides. It's not a line but a parabolic lines, parabolic sides. So this very element can also be expressed as a square element in xy and eta system. We can transform this very irregular shape into a square shape just by transforming in the similar way that we did earlier. So let us say this is 1, 2, 3, 4, then 5, 6, 7, 8 and 9. So these are the nodes. So the corresponding transformed element will be 1, 2, 3, 4, then 5, 6, 7, 8 and 9. Here, regardless of what x1, y1, x2, y2 and so on, the transformed element will have the coordinates same as this one. So this one -1, 3 is 1, 1 and 2 would be -1, 1, 1, 1 minus 1 and this is -1, 1 and this is exactly in between. So this will be 0, 0 minus 1. So 0.9 is 0, 0 and so on. So this is exactly in the middle of these two nodes. Similarly this and this and this, and node 9 is at 0, 0. So what kind of transformation will bring this kind of shape into a square shape like this one? So we'll do transformation here. So what we have to find out is x will be given as summation of n I, then xi eta and xi multiplied by xi. So I equal to 1, 2, 9, because there are 9 nodes, so we can write like this one. And similarly y will be summation from I equal to 1 to 9 ni xi eta multiplied by yi. Okay, this is similar to what we did for the first transformation that we did in the last 2 video lectures. So here however ni will be different because it's higher order. So you can guess that n1, for example, n1 xi eta will be equal to, so we are talking about this one, so we can draw line here, vertical line here, vertical line here, horizontal line here, horizontal line here. So all nodes are covered by 4 lines, 2 horizontal lines or 2 vertical lines. So accordingly n1 will be given by let us say this line first. So this line is this xi equal to 0. So simply we will have xi here, and this line is xi equal to 1. So we will have 1 minus xi term here. Similarly, this is eta equal to 0 term, so we can write eta here, and this is eta equal to 1 or 1 minus eta term will be like this. Now n1 has to be 1 at minus 1 minus 1. So if you put minus 1 here, then minus 1 here, then minus 1 here, minus 1 here, minus 1. So what we get is minus 1 times 2 times minus 1 times 2 is total 4. So this will be 1 over 4. So n1 will be given like this one. So you can see that n1 is quadratic in both. So n1 is quadratic in xi as well as in eta. Yeah. Similarly, we can find out n2 to n9. In every case, there will be 2 horizontal lines and there are 2 vertical lines which will exclude that particular node, and hence the shape functions can be written as we wrote here. So I am not going to write all the other 8 shape function, I am leaving it on you. So this is just one example to show that what we studied, the isoparametric element, can be extended to higher order element like this one. Okay. So I will say and so on. Okay. We can also extend the isoparametric element to the triangular element. So what I mean is, we already studied triangular element, so something like this one. So element node 1 to 3, and we did the analysis. So this is x and y. We had x1, y1 and so on, the coordinates for all these nodes, and we did the analysis. Here when you say isoparametric triangular element, what we mean is, can we transfer that into an element which is something like this. So this element will be transformed to isoparametric element such that one of the vertices will be at 0 0, the other will be at the second one at 1 0, and third one is 0 1, like this one. If we convert like this one, then it may be easier to solve, especially when we have higher order elements. So if instead of this, if our element is 6 noded, let us say 1 here, 1 here, 1 here, then accordingly we get here, here, and here. And then composing the shape functions, how we did in case of this, similar strategy we can follow. We can find out the shape function, all the 6 shape function very easily in that case, and which may be complicated if we don't convert that into an isoparametric element. In any case, this also we need to do. We need to convert from xy coordinate system to say xi1, xi2 coordinate system, okay, so that we can integrate over the triangular element. What I mean is, for integration over the quadrilateral element, we use the transformed coordinate system to integrate. We use the Jacobian matrix and so on, as we did in the last lecture video. For triangular element, there should be equivalent method to find out the integration. When we studied the triangular element, we did not do numerical integration. We just did the integration using equations, the usual integration, what I mean, but we did not perform the numerical integration. So if you want to integrate, do the numerical integration as it is done in computers, then how to find out, for example, shape function of a triangular element, or rather the stiffness matrix of a triangular element by numerical integration. So in order to do that, we need to do this kind of transformation, and we will see that. Okay, so even if it does not make sense now, let us first transform it, and when we do the integration, then we can relate back why it was very important to transform from the usual xy system to xi1, xi2 system. Let's define first the triangular coordinate system. So triangular coordinate system. Okay. So as we have seen earlier, so a triangle which has 1, 2, 3 nodes, and what we saw was n1 was equal to 0 here. If you are on this line, then n1 equal to 0, and if you are here n1 equal to 1. Let's call it the first axis. Let's call it xi, and xi goes from from this line from 2 3 towards 1, meaning that xi 1 is equal to 0, and here at this xi 1 equal to 1. So xi is actually equivalent to n1. On this line, from line connecting nodes 2 and 3, there xi 1 equal to 0 and xi 1 is equal to 1 at node 1. So xi 1 is actually equivalent to n1 only. So we are just writing xi 1 here, but this is equivalent to n1. Similarly for 2, for example, 2, so n2 will be equal to 0, n2 equal to 1 at node 1, and n2 equal to 0 on this line. So meaning that n2 will be equal to 0 at node 1, n2 equal to 0 at node 3. So if we extend this line here on this line, n2 equal to 0. So you can say that xi 2 is equal to 1, and here xi 2 equal to 0. So if we choose xi 1 and xi 2 as two axes, then for a triangle we can have the axis system this way. So we have 1, so you have xi 1 equal to 0, and let us say this is the point where the centroid of the triangle is. There xi 1 will be 1/3, and then parallel line if you draw here, xi 1 becomes equal to 1. So the line between 2 and 3 has xi 1 equal to 0, a line through the centroid but parallel to line 2 3 represents xi 1 equal to 1/3, and parallel line through node 1 will represent xi 1 equal to 1. Similarly, this we can repeat for xi 2. So xi 2 here. So let's just draw separately. So we have like this. So 1 2 3. What we have? 1 3. So this line we have xi 2 equal to 0, and then centroid parallel line, this represents xi 2 equal to 1/3, and then similar parallel line here passing through 2 will represent xi 2 equal to 1. So these are the coordinate systems. So if you have these two coordinates, then we can transform that into this into a xi 1 xi 2 coordinate system. So the original let us say coordinate system, which is xy, and here you had something like this, here 1 2 3, then you will have transformed system where it will be xi 1 and xi 2, and then the corner is where xi 1 and xi 2 meets, meaning that where xi 1 and xi 2 both are 0. Okay. So coming back here, which point has xi 1 and xi 2 0? So if you look here, so xi1 is 0 where? Xi1 is 0 at 1 3, line 1 3. Xi2 is 0 as 1 3, and xi1 is also xi1 is 0 at 2 3. So 3 is common. So looks like point 3 will be the origin because it has both 0, xi1 equal to 0, xi2 equal to 0. Okay. Then since this is a triangle, so if you from point 3 either you go towards direction 2 or direction 3. If you go direction 2, so you will meet the node 2. So this is the value 1. So this one is 0 0 1, and if you go towards xi1 on this xi1 axis, so you will get 1 0, which is node 2. So the transformed triangle is this one. From xy system we have transferred to xi1 xi2 system, where the origin becomes at 3 0 0, and this 1 here. So point 1 becomes 1 0, point 2 becomes 0 1. Once you have transformed from a one triangular element to an isoparametric element like this one, then the next step is to how to find out the shape functions in the transformed coordinate system. So n1 xi1 xi2 will be what? So we want to find out xi1 n1 such that n1 is equal to 0 at node 3 and 2, and it has to be 1 at node 1. So we can straight away write n1 equal to xi1. Why? By doing so, it automatically n1 is equal to 0 at node 2 and 3, and xi1 is equal to 1 at node 1. Similarly, n2 can be directly written as xi1 xi2 will be equal to xi2 only, for the same reason. Xi2 equal to 1 at node 2 and it is 0 at node 3 and node 1. What about n3? So n3 we can simply write is equal to 1 minus n1 minus n2, and will be equal to 1 minus xi1 minus xi2 simply. So these are the three shape functions that we get. Once we have transformed a triangular element from one coordinate system to the usual Cartesian xy coordinate system to an isoparametric system xi1 xi2, the next and once we have the n1 is equal to xi1, n2 equal to xi2, and n3 equal to 1 minus xi1 minus xi2. The next is to formulate the finite element analysis, and for that first we can write x as a function of xi1 and xi2. So this will be equal to x equal to n I xi, okay, I equal to 1 2 3, and similarly y will be function of from summation I equal to 1 to 3, then ni yi. Once we have the relationship between the two coordinate systems, the next task is to find out the area, so or relate the area, in other words. So we know that the area, in order to find out area, we have to know the Jacobian matrix, as we did in the last lecture video. So what is Jacobian here? So Jacobian, for in order to find out Jacobian, we write first say dx is equal to del x over del xi1 d xi1 plus del x over del xi2 d xi2, and similarly dy equal to del x over del y over del xi1 d xi1 plus del y over del xi2 d xi2, or dx dy is given by del x over del xi1 del x over del xi2 del x over del y over del xi1 del y over del xi2. So this is the Jacobian matrix we called J, and here this is d xi1 and d xi2. Okay, so this is the relationship between the variation in these two coordinate systems. So this is what it relates. So in order to find out the area, so d area is given by, as we did earlier, J times d xi1 d xi2. So that's what we found out earlier. So instead of xi1 we had xi, and instead of xi2 we had eta. So but the same relationship you can follow, because it is actually regardless of what kind of coordinate system you have on both the sides, the equations will always turn out like this one. Means the area in terms of this coordinate system will be equal to the determinant of Jacobian matrix multiplied by area in this coordinate system. Yeah, so this is that. So okay, so this is this we can apply, and we have to know the Jacobian. So this is J, this is J here, this is J here. So we have to next find out what the J is. Before we find out J, this also we can rewrite as dA in xy coordinate system will be equal to determinant of the Jacobian times d area in xi1 xi2 coordinate system. Okay, so here it is xy. Now let's look at the Jacobian matrix J we have to find, and for that we have to find out del x over del xi1 and so on. So if let's first extend the expand x and y. So we had earlier x as a summation of ni times xi and so on. So if you write the same thing here, so we have x equal to n1 x1 plus n2 x2 plus n3 x3, and that is equal to n1 is nothing but, we know that this is ny is nothing but xi1. So we get xi1 x1 xi1 plus x2 xi2 plus x3 and n3 is nothing but 1 minus xi1 minus xi2. Okay, so this is equal to what we get? We get x3 plus x1 minus x3 xi1 plus x2 minus x3 xi2. Okay, similarly we can expand y and we get y equal to y3 plus y1 minus y3 xi1 plus y2 minus y3 xi2, and hence del x over del xi1, del x over del xi1 we get x minus 3. Okay, then del x over del xi2 we get here sorry, is this x1 minus x3. So this we get del x over del xi2 becomes x2 minus x3, and similarly del y over del xi1 becomes y1 minus y3, and del y over del xi2 becomes equal to y2 minus y3. So Jacobian matrix J is given by basically x1 minus x3, x2 minus x3, y1 minus y3, and y2 minus y3. So this is the matrix, and hence the determinant of J is given by x1 minus x3 multiplied by y2 minus y3 minus y1 minus y3 multiplied by x2 minus x3. So this is determinant of J. Note that the determinant of the Jacobian matrix here is a constant. So writing dAxy is equal to determinant of J and dA xi1 xi2. If we integrate of this one dAxy, okay, will be area of the triangle is equal to, since J is constant, J we can take it outside, and dA xi1 xi2 you can write, or simply it will be, so you write here dA in xy system will be equal to J times area in xi1 xi2 system. So in xi1 xi2 system we have, if you see here, this is xi1, so 1 here, 1 here, area is 1, half multiplied by 1 multiplied by 1, so half, area is half. So area of this triangle is half, so we can simply write here A xi1 xi2 equal to half. So simply what we get, AXY, or area of the triangle in the xy system, or the actual area of the triangle is AXY, okay, is equal to, we have J multiplied by A xi1 xi2, which is half. So what we get is simply half of the determinant of the Jacobian matrix, or half of the this value that we get. So this is the actual, this is how the area of the triangle. The way we found out the area can be extended to the integration of any function over the triangle. So what I mean to say is, if the original triangle is like this one, so 1 2 3, and there is a function f xy in it, So this is the xy coordinate system, and then you have the equivalent coordinate system xy1 xy2. So this is 3 1 2. So this is transformed. So what I mean to say, if you have to integrate, let us say you have to integrate over the whole area A. So say this domain which one, xy. So let's say omega xy and fx and then d omega. If you write like this one, this if you have to evaluate, this can be given by, so this is omega, this one is omega xy, let's call it this one is omega xy1 xy2. So integrated over omega xy1 xy2, and this is integration f xy. So first you have to convert f into xy. So f as a function of xy xy1 xy2, and y function is a function of xy1 xy2. So you have to convert first x and y into xy1 xy2, and then multiplied by this is gamma high, yeah, and multiplied by j, determinant of j, and d omega. So this is how the conversion will be. So here this integrated over this one, this is also integrated, this one is integrated over this one. However, you have one extra term here, the determinant of the Jacobian, and then it will work. Okay. So any integration in xy can be evaluated by integrating in xy1 xy2 coordinate system, provided you have a determinant of Jacobian term included along with the original fxy. Okay. So now coming back to the Kij that we need to finally be able to determine. So if you remember, for a four noded 2D element, that in xy1 we had xi and eta, and we said Kij is equal to integral k, assuming k constant, a small k, conductivity constant, and then we had this there we used -1 to 1, and then we had del ni over del xi, del ni over del eta, and then we had J inverse transpose term we had, and after that we had del nj over del xi, del nj over del eta, and then we have determinant of the Jacobian and d xi d eta. So this is what we had. Well, this one is for this four noded quadrilateral element. Actually, when it is transformed to xi and eta coordinate system, and the transformed area becomes a square. So in that term, the Kij we calculated in the last lecture video. So same thing I have written here. The how we derive this one, same thing can be repeated actually to derive Kij in this coordinate system. There is nothing different. So both one is x y coordinate system. There is some parameter xi1 xi2 through which x1 and x2 can be expressed, and then just doing integration in the new transformed coordinate system, we are trying to find out the integral in the original coordinate system. So same here we are doing. So meaning that here also the equation remains the same, this is nothing different. However, since here it was a rectangular system, so the two parallel lines, horizontal parallel lines, two vertical parallel lines, so we very conveniently we wrote the limits from -1 to 1. This kind of thing is not there, so we will not write like this, rather we will write for triangular system for this system we have xi1 xi2 instead of xi and eta. That is one difference. Second thing is we cannot write like this one because here we don't have the parallel the sides. So instead of separating this, we will just integrate that as a small area dA only. So we can write kij is equal to a small k, and then integral over omega xi1 xi2. So this is omega xi1 xi2 we call it. So integrate over omega xi1 xi2, and then this can be repeated now. So we will write del ni over del, instead of xi we will have xi1, del ni over del xi2, instead of eta we have xi2, then J inverse, we will have J inverse transpose, we will have, then multiply with del nj over del xi1, del nj over del xi2, okay, and del then you have the determinant of the Jacobian matrix, and then you have d omega here, okay. So this is exactly the same, however we have combined d xi times d eta as an area, basically infinitesimal area, and this has to be integrated over the whole domain here in the transformed coordinate system. In this particular case, as we know J is a constant matrix, as we have seen here. So all these things are known, so J is a constant. So and in general all the derivatives with respect to xi1 xi2 are constant, because all n1 n2 n3 all are linear in xi1 xi2 xi3. So that means this will be a constant, this will be constant, this constant, these are all constant. So that really means that what you get is everything, you can take them out and simply replace it by half times. So we can write it since, let's write it here, like say since J is constant, is a constant matrix for three noded triangular element we being transferred from here to here. So for this one what you get is kij equal to k times ni over del xi1 del n I over del xi2 j inverse j this multiplied by j over del xi1 del n j over del xi2 and j, right, and then all these things, everything is constant, so it's going out of the integration, and then we have to simply this area, so multiply by total area, so total area is half basically. Yeah, so we just write half multiplied by half. So Kij will be simply this one. But let us assume that these were not constant but a function of xi1 and xi2, which will happen in case of let's say 6 noded element, for example. So one here, one here, one here as the existing one, and then let us say middle point of all these sides also have a node. So in that case n1, n2, n3 will be quadrating in xi1, xi2. So in that case, if you take the derivative, still xi and eta will be there. So that means if we write in general, if we write Kij equal to this xi1, xi2, and here let's write it as Fij, then xi1, xi2, and then if you have like this one, and then d omega. If Kij Ij in this term, or any function, any integration is of this function, is something like this, in that case how to find out the this integration. Yeah. So instead of writing Kij, let's say in general, if it is omega xi1, xi2, and we have a function f xi1, xi2 and d omega. If we had to find out this one, then how to find out? So this we have to work in triangular coordinate system. So we can again use the same principle as the Gauss quadrature formula here. However, for triangular system it has different system. So that in triangular coordinate system, I will be given by again the similar to earlier. So this will be equal to Wi, this is weightage I, and then function. So f xi1, xi2, and write I here. So ith xi1, ith xi2. So this is how it will be equal to I equal to 1 to number of Gauss points. So this is integrated as if it is a linear one. Yeah. So it does not have two summation here. It is single summation it can find out. So for example, if ng equal to 1, let's say, so I will be given by w1 times function evaluated at xi1, first xi1 1 and xi1 1, xi1 2. So at these points. So and what is the value of w1? So w1 has to be equal to half. So why? W1 will be half, so that let us say if you have f equal to 1, then if you have f equal to 1, then I has to be equal to area only. So I equal to integral d omega and computed over the whole domain. So it will be just area, I equal to area. So in that case we should have w1 equal to half, hence you have half. So w1 equal to half, and then the what is xi1 and xi2, this has to be the centroid of the. So for centroid we have xi1 1 is equal to 1/3 and xi1 2 is also equal to, so let's write it here. So xi1 2 also equal to 1/3, and hence in this case we simply get half multiplied by function and what 1 3 1 3 in xi1 xi2 coordinate system, and then we get the whole integration. Okay, let's see what happens when n is equal to 2. If n is equal to so I if n is equal to 3, okay, so since this is a triangle, so this can be either 1 like here, or the next will not be 2, n is equal to, it will be rather 3. So this is when n is equal to 1, then it will be n is equal to 3. So in that case there will be 3 points. So there will be 3 points. So how? So let us say this is at this point, and this point, right? So the ng after ng equal to 1, it will be ng equal to 3, but not 2, because it has to be symmetric basically somehow. So since there are 3 vertices, so there will be 3. There has to be 3 points, otherwise 2 will not make sense. So if n is equal to 3, so then the w, we write I as a function of w1 f xi1 xi2 plus w2 f xi2 xi1 xi2 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 2, then plus w3 f xi3 1 xi3 2, where w1 is equal to, again if you assume, if all everywhere the function f is 1, in that case the integration should converge to half, which is the converge to half, as in the transform coordinate system the area is half. So basically, so the w1 will be equal to 1/3 of half, so basically 1/6, and which is equal to w2 equal to w3, all of them will be equal to 1/6, and xi1 1 will be equal to 1/6, xi 1 2 also 1/6, then xi 2 1 is equal to 4/6, xi 2 2 equal to 1/6, and then xi 3 1 is equal to 1/6, and xi 3 2 is equal to 4/6. So these values can be memorized actually to find out the integration in the triangular coordinate system. Similarly, for a higher number of integration points, these values of wi and xi I1 and xi I2 are known and can be got from standard books. So for example, the higher number of points will be when n equal to 4, for example. Then next will be n equal to 6 or n equal to 7, so all symmetric. So 4 means you have 3 points here and then here as well. 6 will be something like here you have, and like this, and this is 6, and 4 7, same as 6, but there will be in middle as well, so like this. So this is 7. So just for demonstration purposes only, but the basic method remains the same. The only difference between this and the that we used for the square element, the transformed square element, is that there it was two-dimensional. Here this is treated as if it is one-dimensional only. So this integration we are doing as if it were a integration along only one axis, as we did when we integrated for 1D cases we did in the classroom before the midsem exam. I should also mention here, if we assume xi 3 is equal to 1 minus xi 1 minus xi 2, which is akin to n3. So if we have like this one, in that case integration also can be got directly from a formula, and the formula is this is integrated over the whole domain of xi 1 xi 2 domain. Okay, and here any function f, so let's say I equal to any function of xi 1 xi 2 and d, this if we have to find out, then this also can be if xi 1 xi 2 can be expanded such a way that this becomes equal to, let us say, integration xi 1 xi 2, and then you have says some coefficient, let us say alpha times xi 1 and power, let us say the power is I, then xi 2, these are the real powers, so these are then 3k. So these ijk are not the superscript for identification purposes, but the real powers. Basically these are the powers. So this integrated over d omega, plus there will be a beta which is also will be the similar the xi 1 xi 2, and then there is again written like this one only in terms of powers. If we can expand this to something like this one, then we can find out the integration I just by using some formula. And what is the formula? The formula is so this xi 1 xi 2, okay, and then xi I 1 xi 2 to the power j and xi 3 to power k d omega is equal to, so I am writing here, is equal to I factorial j factorial k factorial divided by I plus j plus k plus 2 factorial, okay, factorial, multiplied by 2 times area. So 2 times area multiplied by 2 times area. So integration of xi1 to the power I, xi2 to the power j, xi3 to the power k integrated over the whole transformed triangle is equal to I factorial, j factorial, k factorial divided by I plus j plus k plus 2 factorial, whole of it factorial, multiplied by 2a, where a is the area of the element, here 2ae. So this is the area in the transformed coordinate system, which is half. So this equation you can find in your textbook. You can have a look at it. Okay, see you in the next lecture video.